Welcome back to the Deep Dive. Today, we're shifting gears a little. We aren't just exploring a topic, we are stepping into a role.
Right.
So I want you to close your eyes for a second, unless you're driving, of course, in which case, please don't. And just imagine the environment.
Okay.
You've just walked into a glass-walled conference room, top floor of a skyscraper in, say, Stuttgart, or maybe Detroit or Tokyo.
I'm picturing it.
You are a senior technical strategy consultant. You work for one of the world's most prestigious automotive engineering firms.
It's a high-pressure room.
Yeah.
The coffee is probably expensive, but the mood is tense.
Exactly, because sitting across that table is your client, a major legacy automotive OEM.
A big one.
Massive, historic, and right now they are sweating. They're watching their competitors, companies like BYD, tech giants like Huawei, roll out these incredibly compact, incredibly efficient electric powertrains.
And they're looking at their own architecture, the one they just spent billions developing.
And they're realizing it might already be obsolete.
Oof. Yeah, they're seeing the writing on the wall. The era of, good enough is just, it's over. The efficiency wars have begun.
So your mission, which we are going to execute together over the next hour or so, is to deliver a comprehensive technical strategy report.
Got it.
The title on the cover reads, Global EV X-in-1 Electrification Integration.
X-in-1. It sounds like a bit of a marketing buzzword, doesn't it? But in our context, it represents a really fundamental shift in how we build cars.
It really does.
Yeah.
And to keep this rigorous, because we are expensive consultants, after all, we're going to use a very specific framework.
Okay.
We're taking a McKinsey-style top-down approach, and we're going to adhere strictly to the MEC principle.
Mutually exclusive, collectively exhaustive.
The gold standard. It means we're going to cover the entire landscape without any overlapping redundancies. We'll look at the market context, then the engineering challenges, what we're calling the triangle of pain, and finally the silicon solution.
Sounds like a solid plan.
So let's start where any good report does, the executive summary. If the CEO of this car company looks at you and says, give me the bottom line, what's the core thesis here? What do you tell them?
The thesis is this. The industry is undergoing a violent shift from physical integration to silicon-level integration.
A violent shift. I like that.
It is. If you are still just bolting metal boxes together, you have already lost. The future is one-chip control.
Okay, let's unpack that immediately because that is a very bold claim. Physical versus silicon. What's the real distinction there?
So physical integration is what we've seen for, the last 5 years. It's what we call package integration.
Right.
You take the inverter, the charger, the DC-DC converter, and you basically just bolt them together into a single casting.
You might share a cooling loop, a housing.
Exactly. You share a housing, maybe a cooling plate, but inside it's still 3 separate brains. 3 separate microcontrollers, probably talking to each other over a CAN bus. It's not true integration.
So it looks integrated from the outside, but inside it's still kind of a fragmented mess of wires and signals.
It's a condominium complex. That's the best analogy. Everyone lives in the same building, but they all have different keys and they barely talk to each other.
I see. And silicon-level integration.
That's completely different. It's taking the brains of all those disparate systems and merging them, actually fusing them, onto a single piece of silicon.
So one single processor.
One processor running the motor, the charging, the battery management, and all the thermal loops, all at the same time.
And so what? Why does the client sitting across that table need to care about this architectural nuance right now?
Because the battlefield has shifted
Okay.
completely. For a decade, the big war was about battery chemistry.
Right. Who has the best energy density, the lowest cobalt?
Exactly. But now batteries they're commoditizing. The new war is architecture efficiency.
Okay.
The winner isn't just the one with the longest range anymore. It's the one with the lowest total cost of ownership, the TCO, and the highest assembly efficiency.
So if our client is out there buying 3 separate chips and soldering them onto 3 separate PCBs while BYD is printing one board with one chip,
Then your client has a higher bill of materials, a heavier car, and a much slower assembly line.
they lose on margin and they lose on price.
Every time.
Stark. I love it. Okay, let's dive into part 1, the market context. We keep saying X-in-1. Let's clarify the X for the client. What exactly are the organs we are trying to transplant into this single body?
It is a bit of an alphabet soup, isn't it? But every automotive engineer knows these acronyms by heart.
Let's run through them.
Okay, let's start with the big three. You have the inverter, that's the heart, pumping energy to the motor.
Right.
You have the OBC, the onboard charger, which takes AC from your wall socket and converts it to DC for the battery.
And the DC-DC converter.
Yep, which steps that high battery voltage way down to 12 volts for your lights, your radio, all the low voltage stuff.
And that's the classic 3-in-1 that we saw first.
That was step one. But the X is expanding. Now we're seeing 7-in-1, even 8-in-1 systems.
So what else is being pulled in?
We're adding the BMS, the battery management system, the PDU, your power distribution unit, basically a smart fuse box, the VCU, the vehicle control unit.
The overall brain of the car.
In many cases, yes. And critically, the thermal management system.
Thermal management, so you mean the air conditioning and the coolant pumps?
Yes. And that is a huge addition because, well, thermal is complex. So just imagine a single box that takes power from the grid, charges your battery, manages the health of every cell, converts the voltage for the radio, spins a motor, and cools the entire system.
It sounds like a monster. Is this actually real? I mean, is this on the road, or is this just something suppliers are showing off at trade shows to look cool?
Oh, it is very real, and it is on the road today. We need to show the client the BYD case study.
What are they doing?
Over 50% of their new battery electric vehicle models are already equipped with 8-in-1 systems.
50%. Wow. That's not a pilot program. That's their standard.
It is their standard, and it makes sense for them. BYD is vertically integrated. They make their own chips, their own batteries, their own motors. They figured this out early. If you integrate, you win.
And what about Huawei? They're a big player now.
Huawei's Drive One system is a great example of a 7-in-1 deep integration. They've managed to reduce the PCB count drastically.
And that matters because...
Well, think about it. Instead of paying for 6 printed circuit boards, 6 metal housings, 6 sets of expensive high-voltage connectors, you pay for 2, maybe 3.
That's a huge cost saving, which leads us right to the drivers. Why are OEMs pushing so hard for this? You mentioned cost, but let's break it down for them.
Okay, there are 3 main drivers. First, the physical. Let's call it chassis synergy.
What does that mean in practice?
It means when you eliminate those thick, heavy, bright orange, high-voltage cables that run between the charger and the inverter.
The ones that are super expensive and heavy.
Exactly. You save a ton of weight, you save space, and that means you can package a bigger battery or maybe just have a lighter, more efficient car overall.
Copper isn't cheap, and it's certainly not light.
Precisely. The second driver is economic. Reduced bill of materials, or BOM.
Right.
If you can share a digital signal processor, a DSP, between the motor control and the power factor correction for the charger, you don't need to buy 2 separate chips.
You buy one slightly more powerful one.
Which is almost always cheaper than 2 separate ones. You also save on the housing, the connectors, the gaskets, the seals. It all adds up.
Okay, so physical and economic. What's the third driver?
Production. This is the one the manufacturing guys absolutely love.
Why is that?
Think about the assembly line. If a robot has to install 8 different boxes, bolt each one down, and then plug in 30 different wiring harnesses, that's a really slow station.
A bottleneck.
A huge bottleneck. Now, what if that robot just lifts one single 8-in-1 unit, bolts it in, and plugs in, say, 3 main cables?
Your throughput just skyrockets.
You've just shaved minutes off the takt time. In the world of automotive manufacturing, that is worth millions and millions of dollars.
Okay, so faster cars to drive, cheaper cars to build, and faster cars to assemble. If I'm the client, I'm probably thinking, this is a no-brainer. Where do I sign? But as a consultant, I know that when something sounds this good, there's always a catch.
There's always a catch. The complexity doesn't just disappear, it just moves.
Where does it go?
We are taking all the complexity out of the wiring harness and we're shoving it all inside one single box.
Which brings us neatly to part 2 of our report, the engineering triangle of pain. I love this title.
It's accurate.
We're going to break this down, MCE style. We have physical pain, logical pain, and safety pain. So let's start with the physical. What is the big downside of putting everything in one box?
The biggest physical pain, by far, is the serviceability dilemma. It's the all-or-nothing risk.
Walk me through a scenario, a real-world example.
Okay. Imagine a customer. They have a brand new EV. They love it. But one day, the onboard charger fails. And it's something simple. Maybe a generic $5 capacitor blows on the AC input filter. In a traditional distributed car, the mechanic unbolts the charger, puts in a new $400 unit, and the car is fixed in an hour.
Simple enough. But in an 8-in-1.
In an 8-in-1, that charger is physically fused inside the main powertrain housing. It might share a cooling plate and a seal with the inverter. You cannot just pop it out.
So what do you do?
You might have to replace the entire electric axle, the whole assembly.
So you are swapping out a $3,000 or $4,000 unit because of a $5 component failure?
Exactly. And who pays for that? If it's
Right.
under warranty, the OEM pays for it. This drives warranty costs through the absolute roof.
It's a logistical nightmare, too.
A complete nightmare for dealerships.
Yeah.
Do they now have to stock these giant, heavy axles? Do they need clean rooms to open these sealed units up? The answer is usually no.
That is a massive total cost of ownership risk that they need to factor in.
A huge one.
Okay, what about the other physical challenge you mentioned? Thermal complexity?
This is just physics fighting against you. We are putting a toaster, the OBC, a furnace, the inverter, and a very sensitive computer all in the same small metal box.
And they all have completely different thermal needs, I assume.
Drastically different. The inverter uses silicon carbide switches, Sisaki, that get incredibly hot, incredibly fast. We're talking hundreds of degrees in seconds.
Right.
The BMS electronics, on the other hand, the things measuring the battery cell voltages, need to be kept cool and stable to get an accurate measurement. If you have hot spots where that inverter heat bleeds over into the BMS section of the PCB...
You get measurement drift, your state of charge estimate goes out the window.
Exactly. And what about the plumbing? The liquid cooling?
What's the problem there?
Well, to cool all these different components effectively, you need a really complex, labyrinthine network of cooling channels inside the housing. This creates a very high pressure drop.
Meaning the pump has to work harder.
Your coolant pump has to work much, much harder to push the fluid through that maze. That's a parasitic load. It eats directly into your vehicle's range.
So physically, it's a nightmare of heat and serviceability. Okay. Let's move to the second point of the triangle, the logical layer. You called this the time loop paradox. This sounds like something out of science fiction.
It feels like it to the software engineers who have to solve it. We are basically trying to run different speeds of life on a single brain.
Give me the tortoise and the hare comparison. What's slow and what's fast?
Okay, so thermal management. That's the tortoise.
Right.
Heating up a battery pack or cooling down a cabin takes minutes. Adjusting a coolant valve might happen once every second. That's a 1-second loop.
Which for a computer is an eternity.
An absolute eternity. Now, the hare, that's the inverter.
Yeah.
To spin an electric motor smoothly, especially using something like field-oriented control, you are calculating current vectors and adjusting the magnetic field every 50 to 100 microseconds.
Brosa. Mitris. Yeah.
It is blazing fast.
So you have one task that needs attention once a second and another that needs it.
Right.
What, 20,000 times a second?
And they are fighting for the exact same CPU resources. The technical challenge is called interrupt latency.
Explain that.
Imagine the CPU is deep in a complex thermal calculation. Maybe it's figuring out the optimal valve position for the cabin heater to prevent fogging the windows. And suddenly, the inverter task interrupts and screams, I need to switch this transistor N now W or the motor is going to stutter.
And if the CPU is too busy thinking about the heater?
You miss the motor control deadline, you get torque ripple, the driver feels a shudder through the car, or worse, you lose control of the current for a moment and you could blow a fuse or damage the motor.
So the logical challenge is just ensuring the slow, heavy tasks don't clog the pipeline for the fast, safety-critical ones.
That's it in a nutshell.
Which leads us perfectly to the third, and frankly the most terrifying point of this triangle, the safety layer. This is what you call the critical pivot of our entire report.
This is where the consultant really earns their fee. Because now we have to talk about mixed criticality.
Let's define that for the client. We're talking about ACell levels, right?
Yeah.
From ISO 26262.
Yes. The Automotive Safety Integrity level. It's a risk classification scheme. It ranges from QM quality management, which basically means no safety requirement, all the way up to ACell D.
And ACell D is?
ACell D is life critical. It means a failure could lead to severe or fatal injury.
So in our theoretical 8-in-1 box, who holds which rank? Let's assign them.
Okay, easy. The inverter is ACell D. No question. If the inverter goes rogue and commands full unexpected torque when you're at a stoplight...
You're in the intersection. People could get killed.
Exactly. Highest level of risk. The onboard charger is usually ACell B. It handles high voltage from the grid, so fire is a real risk, but it's mostly active when the car is parked and unoccupied.
Okay, so a lower risk level. And the new additions, what about thermal?
Thermal management is often just QM. Maybe ACell A in some specific cases. It's important for comfort, for battery life, for efficiency. But if the AC stops working, nobody dies immediately.
So we have an ACell D life critical system. sitting right next to a non-critical QM system on the same piece of silicon.
And here is the nightmare scenario we need to present to the client.
Lay it on me.
Imagine you have a memory leak in the non-critical thermal management application. A junior developer wrote a sloppy line of code for the cabin heater logic. It starts eating up memory, bit by bit,
Yeah.
and eventually it overwrites a variable in a memory address that belongs to the inverter.
And the inverter is sharing that same brain, that same RAM.
Correct.
Yeah.
The inverter task wakes up, tries to read its torque request value from memory, but it finds garbage data because the heater app scribbled all over it.
So the inverter crashes.
The inverter crashes, and you are driving down the highway at 70 miles per hour, and your propulsion system suddenly reboots because the air conditioner had a software bug.
That is completely unacceptable. The client would be sued into oblivion.
It's the ultimate failure mode,
Ah.
and this introduces the absolute 100% non-negotiable requirement for this entire technology to work.
Which is
Freedom from interference, FFI.
freedom from interference. It means you have to keep the bad code, or the buggy code, away from the good, safety-critical code.
You have to build walls.
Now, traditionally, how have we done this? Because my laptop runs Spotify and a spreadsheet at the same time, and if Spotify crashes, my spreadsheet usually stays open.
Right. In the PC world, and even in things like automotive infotainment systems, we use software virtualization. We use a hypervisor.
Which is a piece of software that creates these virtual walls between applications.
Yes, it's like running a simulation inside a simulation. But here's the fundamental problem with using hypervisors for ASIL-D safety.
What is it?
First, they have overhead. They eat up valuable CPU cycles just managing the walls. But second, and much more importantly, the hypervisor itself is just more software. What if the hypervisor has a bug?
Then the walls themselves disappear.
Exactly. For a life-critical application, relying solely on a software wall is often considered far too risky. Proving to a safety auditor that your hypervisor software is 100% bug-free is incredibly difficult and incredibly expensive.
So we've painted a pretty grim picture. Physical integration hurts serviceability, logical integration creates timing conflicts, and safety integration risks catastrophic failure. The client is looking at us like we just killed their entire project. Let's save it. Part 3, the solution.
Okay. Enter the concept of integration by silicon. And specifically, we need to look at a hardware-first strategy, like the one NXP Semiconductors is pushing with their S32 processor family.
NXP is a heavyweight in automotive silicon. What is their answer to this hypervisor problem?
Their answer is simple and it's elegant. Don't use software to do a hardware job.
Oh.
They have introduced a technology built into their chips called the XRDC, the Extended Resource Domain Controller.
That's a mouthful, XRDC. What is it? Essentially.
It is a physical hardware firewall that is built directly into the silicon of the chip. It's not software. It sits on the bus between the processor cores, the brains, and all the peripherals.
Other peripherals.
The memory, the GPIO pins, the timers, the communication interfaces, everything the core talks to.
How does this differ from, say, the memory protection units or MPUs we've had for years?
An MPU is a good start, but it usually just checks which core is making the request. Okay.
Yeah.
Your core 1, you're allowed to access this block of memory. The XRDC goes much deeper.
How so?
It acts as a gatekeeper at the bus level. It doesn't just check the core, it checks the task ID of the software that's running.
Wait, so it knows which specific task is running on the core at that exact moment?
Yes. It assigns a hardware ID to every single transaction on the internal bus.
So let's go back to our nightmare scenario.
Yeah.
The thermal management task, which is QM level,
Tries to write data to the inverter memory address, which is ASIL-D. The XRDC sees this transaction come onto the bus. It sees the ID mismatch, and it says, hey, you are the thermal task. You are not allowed in the inverter safe. Access denied.
and it blocks it.
It physically blocks the transaction right there on the bus.
Does the CPU have to stop and handle this error? Is there an interrupt?
No. And that is the absolute beauty of it. It happens entirely in hardware. It has zero CPU overhead. The bad transaction just, it bounces off the wall.
So the thermal app might crash?
The thermal app might crash, sure, it gets a bus fault. But the inverter, the ASIL-D task, it keeps spinning. It doesn't even know the attack happened.
Yeah, it is the aha moment. True freedom from interference, enforced by physics, not by code.
It's the only way the chief engineer is going to sleep at night. It allows you to confidently run mixed criticality workloads without that constant fear that the low priority stuff is going to kill the high priority stuff.
Okay, so this is huge. We have the S32 chip with this XRDC firewall. But simply having a powerful chip isn't enough. You need to be able to program it and configure it. Which brings us to part 4, the Flex Foundation platform.
Right. Flex Foundation is the whole ecosystem that NXP has wrapped around the chip itself. It's designed to address the sheer complexity of setting all these domains and firewalls up correctly.
Because I have to imagine that configuring a hardware firewall like this manually is, well, it's extremely error-prone.
It's a recipe for disaster. Imagine a software engineer typing in thousands of hexadecimal memory addresses by hand into a configuration file.
You'd make a typo.
You're guaranteed to make a typo. Did I type 0 by 400 or 0 by 404? If you get it wrong, you might accidentally lock your own inverter task out of the timer it needs to function.
So how does Flex Foundation solve this problem?
They provide a configuration tool. This is part of what they call Pillar 3 tools that is completely visual. It allows you to literally drag and drop peripherals between domains.
You're kidding? Drag and drop.
Yes. You see a graphical list of all the timers on the chip. You click on timer A and you drag it and you drop it into the inverter domain box on your screen. You drag ADC channel 1 and you drop it into the thermal domain.
And the tool does what?
The tool then automatically generates all the complex underlying configuration code to set up the XRDC registers perfectly.
So it sort of democratizes functional safety. You don't need to be a memory map wizard to set up a safe and secure environment.
Exactly. It's designed to prevent those kinds of manual coding errors that can be so dangerous.
There was another piece of hardware mentioned in the platform, something called the CoolFlux DSP. Is that just a fancy marketing name, or is it doing real work?
It's a dedicated workhorse. Remember we talked about the time loop paradox earlier?
The inverter needing to do all that math every 50 microseconds.
Yes. Well, modern motor control is basically just advanced trigonometry on repeat. Sine, cosine, Park transforms, Clark transforms. It's very, very heavy math.
And if the main CPU has to do that?
If the main CPU, which is an ARM Cortex core, has to stop everything it's doing to crunch trig every few microseconds, it slows down everything else. It can't check safety monitors or handle communication.
So CoolFlux is like a math coprocessor, a dedicated calculator.
It's a dedicated hardware accelerator specifically for that kind of math. It sits right next to the main CPU. The CPU just says, here are the latest current values, give me the voltage vector. The CoolFlux crunches the trig almost instantly and just hands the result back.
So it offloads the heavy lifting.
Completely. It frees up the main CPU to handle the high-level logic and, more importantly, the safety-critical checks. It's all about efficiency.
It all comes back to efficiency.
Squeezing every last bit of performance out of the silicon.
All right, consultant. We've covered the high-level strategy. The CEO is on board. Now I want to get into the weeds, part 5. The detailed safety architecture. The client's chief engineer, let's call him Dr. Weber, is sitting there with his arms crossed. He wants to know exactly how we keep this system safe. Let's walk him through the 3 main components: inverter, OBC, and DC-DC. We'll examine the safety mechanisms and the safe states.
Let's do it. Let's start with the big one, the inverter, ASIL D.
What is the primary safety mechanism for ASIL D?
It's lockstep cores. This is the industry gold standard for ASIL D compute. You don't just run your critical code on one processor core, you run it on 2 cores simultaneously.
Like identical twins mimicking each other's every move.
That's a great way to put it. They receive the exact same inputs, and they execute the exact same instructions at the exact same time. Often, one is delayed by a single clock cycle to prevent common cause failures, like a voltage dip hitting both cores in the same instant.
And they're constantly comparing their answers.
Constantly. There's dedicated hardware logic that compares the output of core A and core B on every single cycle. If core A says apply 50% torque and core B says apply 51% torque, the system knows instantly that something is very wrong.
And it triggers a fault.
Immediately.
Okay, so a fault is triggered. Now, what is the safe state? This is crucial. If I'm doing 100 miles per hour on the Autobahn and the inverter fails, you can't just turn it off, right? That seems dangerous.
You absolutely cannot. If you just turn off all the inverter switches, what's called open phase, at high speed, the spinning motor acts like a powerful generator.
Right, regenerative braking.
But uncontrolled. It produces a massive back EMF, an electromotive force. That voltage can spike way higher than the battery's voltage. It can destroy the inverter's expensive transistors and even damage the battery pack.
So what do you do instead?
You perform what's called an active short circuit, or ASC.
You short the motor. On purpose. That sounds bad.
It sounds completely counterintuitive, I know, but yes. You deliberately turn on all 3 of the bottom switches, or all 3 of the top switches, of the inverter bridge. This shorts the three phases of the motor together.
And what does that do electrically?
It forces the current that the motor is generating to circulate internally within its own windings. It creates a strong braking torque, so the car slows down safely. But most importantly, it clamps the voltage. It prevents that dangerous voltage spike from ever reaching the DC bus.
So you're sacrificing the car's kinetic energy to save the electrical architecture.
That's the trade-off.
Hmm.
But you only do this at high speed.
Why not at low speed?
At low speed, an ASC could cause a really sudden jerky stop, which could be dangerous in itself. So at low speed, the safe state is different. It's safe pulse off, or open phase, you just let the car coast to a stop. The system has to be smart enough to choose the right safe state based on the motor's RPM.
Fascinating physics. Okay, let's move to component number 2. The onboard charger, the OBC, ACEL-B.
The standard topology we're seeing here is the totem pole PFC.
Why is it called a totem pole?
It just refers to the way the transistors are stacked vertically on top of each other in the circuit schematic. It looks like a totem pole, but the key here is efficiency. Old chargers used a diode bridge rectifier to convert the AC from the wall into DC. Diodes have a forward voltage drop. They waste a lot of energy as heat. A totem pole design uses active switches like MOSFETs or GaN transistors to do the rectification. It's way, way more efficient.
And what are we monitoring for safety?
We're constantly monitoring the AC voltage and current from the wall, the DC voltage and current going to the battery, and something called THD, total harmonic distortion.
Why do we care about THD?
Because the grid is a two-way street. If your charger is poorly controlled, it can act like an antenna, injecting high-frequency noise and harmonics back into the power lines.
And that could affect other things in my house.
It could make your neighbor's LED lights flicker, or worse, mess with the utility company's transformers. The grid operators have very strict rules about this.
So what's the safe state for the charger if it detects a problem?
Immediate isolation. Open the main AC breaker, the relay. Physically disconnect the car from the wall, no questions asked.
Simple and effective. Okay, finally, the DC-DC converter. You said ACLC for this one. This is the bridge between the high-voltage battery 400 or 800 volts and the little 12-volt system.
The absolute key word here for safety is isolation monitoring.
Why is that so critical?
Because you have a massive potential difference. Let's say 800-volt sitting millimeters of plastic away from the 12-volt system that touches everything the user interacts with.
The dashboard, the radio buttons, the USB ports.
All of it. If that isolation barrier ever breaks down,
the 800 volts jumps over to the 12-volt rail.
And the dashboard could literally explode. The USB port becomes lethal. It's a catastrophic failure.
So the DC-DC isn't just converting power. Its main job is to guard that gate.
It is constantly actively measuring the insulation resistance between the high voltage side and the low voltage side. If it detects even a tiny micro leakage current, it shuts down instantly.
And it also does the standard protections.
Of course, over voltage, under voltage, over current protection to make sure the sensitive 12-volt electronics don't get fried.
That is a satisfyingly deep dive into the safety details. Dr. Weber should be happy. But let's zoom out again. A chip is just a brain. It can't act without a nervous system and muscles. Part 6. The one-stop shop ecosystem.
Right. NXP's pitch to the client here is, don't just buy our microcontroller. Buy the whole nervous system that's designed to go with it.
What are the other key organs in this system?
First and foremost, the power management IC, specifically something like the FS26 Safety SBC. That stands for System Basis Chip.
I always hear about SBCs. What do they actually do for this system?
Think of the SBC as the watchdog. Its first job is to provide clean, stable power to the main S32 processor. But its more important job is holding a leash.
A leash.
It's constantly challenging the processor. It asks, are you alive? Solve this simple math problem for me. It's a challenge response protocol.
And if the processor doesn't answer?
If the S32 processor freezes or gets stuck in an infinite loop, and it doesn't answer correctly within a certain time window, the SBC says, you are compromised. And it pulls the leash. It cuts the power or triggers a hardware reset of the main chip.
So it's the ultimate failsafe if the main brain goes completely crazy?
Exactly.
And what about the muscles, the components that actually switch the high voltage for the motor?
Those are the date drivers. A part like the GD316X. These are critical little chips that sit between the low voltage microcontroller and the huge high voltage silicon carbide switches.
And they need to be isolated.
They need robust galvanic isolation because one side is talking to the 5-volt logic of the microcontroller and the other side is physically touching the 800-volt bus.
So the strategy we're recommending to the client is reduce your integration risk by buying a family of parts that are already designed and validated to talk to each other.
Exactly. If you buy a microcontroller from vendor A, a watchdog from vendor B, and a gate driver from vendor C, you might spend the first 6 months of your project just debugging the communication between them. If you buy the pre-validated ecosystem, you can get straight to writing your application code.
Which leads us perfectly into our final section, part 7, the implementation strategy. We have the technology, we have the ecosystem. How do we build it fast? Our client is behind schedule. They need to catch up to BYD, and they need to do it yesterday.
We need to recommend the modular platform concept.
Explain this. How does it differ from the traditional way of designing these electronics?
Okay, traditionally you design one single massive PCB with everything on it. The inverter, the charger, the DC-DC, all soldered down. It's elegant when it's finished, but it's incredibly risky during development.
Why?
What if, halfway through development, you decide to switch from IGBTs to the newer silicon carbide switches for your inverter to get more efficiency?
You'd have to scrap the whole board design.
The whole board. Reroute everything. Redo all your thermal simulations. It costs months of time and hundreds of thousands of dollars.
So what's the NXP approach?
It's a motherboard plus daughter card approach. You have a main motherboard that has the S32K39 brain and all the common power supplies. Then the inverter is on a separate plug-in daughter card. The DC-DC is on another separate plug-in card.
It's like building a high-end gaming PC. You can swap out the graphics card without throwing away the whole computer.
That's the perfect analogy. If you want to upgrade the inverter performance for a new model year, you just spin a new, better inverter daughter card. The motherboard stays the same. The core software on the motherboard stays mostly the same.
So it accelerates prototyping and allows for derivative models.
Exactly. You can have a performance inverter card for your sports model and a cheaper economy inverter card for your base model, and they both plug into the same motherboard. Massive reuse.
And what about the long-term roadmap? We mentioned 2 chips, the S32K39 and the S32K5.
This is vital for the client's long-term strategy. The S32K39 is what's available now. It's powerful and perfect for a 3-in-1 system. Inverter, OBC, and DC-DC.
But the future is 8-in-1.
The future is 8-in-1, and for that you need the S32K5, which is the future beast designed for that massive high integration workload.
And the software transfers over.
That's the key. The core architecture is consistent. The code you write and validate today for the K39 will, with some adaptation, run on the K5 tomorrow. This software reuse is where the real long-term money is saved. You aren't reinventing the wheel for every single vehicle generation.
There's one last point here that I think is critical for a strategy report. The paperwork. The certification.
Ah, yes. ISO 26262, the bane of every automotive engineer's existence.
It's incredibly expensive and time-consuming.
Which is why NXP offers what they call safety SEOC documentation. That stands for safety element out of context.
What does that mean in plain English?
It means they basically hand you a binder full of pre-certified documents from the safety assessors. Here is the functional safety concept, the FSC, for this chick. Here is the independent proof that the XRDC hardware firewall actually works as advertised.
So you don't have to start from scratch and prove it all yourself to the auditors at 2.
You still have to prove your overall system-level safety, of course, but the component-level safety case is already done for you. It's a paperwork shortcut that can shave months off your certification timeline.
Okay, we have built a solid, comprehensive report here. Let's head to the outro and summarize this for the client. We need to leave them with clear, actionable takeaways. What are the 3 pillars of our final conclusion?
Takeaway number 1, inevitability. X-in-1 integration is not a fad. It is the only viable path to meeting future cost, weight, and assembly speed targets. If you don't integrate, you simply cannot compete on price. Period.
Takeaway 2.
The safety baseline, hardware isolation, specifically a technology like the XRDC, is the non-negotiable requirement for making this work safely. Do not let your teams rely on software hypervisors for mixed criticality systems that combine ASIL-D and QM. It is a massive liability just waiting to happen.
And takeaway 3.
The tactic. Use modular platforms and pre-validated ecosystems to survive this transition. Don't be a hero and try to build every single component from scratch. Your competition is moving too fast. Speed is of the essence.
Brilliant. Now, before we sign off and leave the conference room, I have one final provocative thought for them to chew on.
Okay.
We spent a lot of time talking about freedom from interference. If the hardware can now truly and reliably isolate conflicting software, if the brakes are perfectly safe from the air conditioner thanks to a hardware firewall,
Right?
are we moving toward a future where third-party developers could write apps for specific vehicle subsystems?
You mean like an app store for the powertrain?
Exactly. Today, the OEM controls every single line of code with an iron fist. But what if a clever startup in Silicon Valley writes a brilliant AI-driven thermal management algorithm that can increase a vehicle's range by 10% just through smarter cooling?
Wow.
Could they sell that algorithm to Ford or BMW as a plug-in app that runs safely on the main processor?
If the hardware isolation is as robust as we've discussed, then yes. Technically, it is absolutely possible.
Think of the implications.
You could decouple the innovation cycles. The car becomes a platform, just like an iPhone. You go to the store and download the Eco Plus thermal app, and suddenly your car goes 30 miles further on a charge.
But are the OEMs brave enough to open that door, to give up that control?
That is the billion-dollar question, isn't it? It requires a complete mindset shift from being a controller to being a platform provider. But with the hardware we've discussed today, the barrier is no longer physics. It's just politics.
And that is a perfect place to end. Thank you for joining us in the conference room today. We hope this technical strategy report serves you well in your next big engineering meeting.
Drive safe, check your isolation monitoring, and always keep your cores locked in step.
See you next time on The Deep Dive.